In this lecture, we will discuss periodic structures and periodic boundary conditions in finite difference time domain. In a frequency domain method, periodic boundary conditions and modeling periodic structures is a piece of cake. In the time domain, it gets interesting and more involved. So we'll very quickly review what we did last time, and then we'll jump in and talk about just the periodic structures, not even how to model them yet, just the math behind periodic structures, why they're interesting and useful to us. Then we need to discuss periodic boundary conditions in finite difference time domain. This is how we model something that is periodic. And what we'll find is the field in a periodic structure is also periodic, so it becomes redundant then to have 1,000 unit cells in our memory. Why not just one? Because we really have the same answer in each unit cell. However, incorporating those periodic boundary conditions in finite difference time domain gets interesting, and there's some points to this that we need to discuss. And we'll end with how to calculate electromagnetic band diagrams using finite difference time domain, and I'll even introduce what a band diagram is briefly. And we'll go into much more detail in these in the follow-on courses, computational electromagnetics, and then the one following that, 21st century electromagnetics. Let's first review what we did last time. So we talked about methods for incorporating metals into our finite difference time domain models. And I said there's at least 4 ways to do this. The easiest and the least impact on the code is to set the dielectric constant to something ridiculously large, like 100,000, 1 million. And anywhere we do that, it will essentially force the electric field at that point to be 0, or at least be orders of magnitude smaller than anything else. And we've effectively put a metal at that point because the electric fields are forced to be 0 at those points. The next thing we can do is assume perfect electric conductors, and we go into our update coefficients and we make those zeros wherever there's a conductor. This will force, during the updates, it will force the electric fields at those points to also be 0 as if it was in a conductor. Now, we may actually want to account for some conductivity. It's not perfectly conducting. It has some finite conductivity, in which case this is a bit more impact on our code. We need to leave that conductivity term in Maxwell's equations and derive update equations with that in there, and also not getting that confused with the fictitious conductivity terms that we used in our PMLs. And then the last one that we've talked about a bit in this course is the Lorentz-Drude model. And here we can not only account for metals, we can account for very dispersive metals and even dispersive dielectrics. However, that requires even more modification to the formulation and implementation. We talked about placing metals on the grid, and we said for the E mode, since the E mode is tangential to all surfaces always, there's no problems. In the H mode, the electric field is now in the plane of the simulation, and the rule of thumb here is that we want the field component immediately inside the metal to be the tangential field component. So let's say we have these two grids, and in white we have air, and in the gold region we have metal. Here, notice the fields immediately inside the metal are perpendicularly polarized to the interface. This is bad. This will lead to very, very slow convergence. A better way to do that is to offset this by a half cell, and now notice the fields immediately inside the metal are tangential to the interfaces. This will converge much faster. We can get away with much coarser grid resolution doing it that way. And then we can ask the question, well, what if we have a curved metal surface? And so the quick answer is do the best you can with this rule. If not, in the literature there is lots of discussion about how to incorporate metals and curved metal boundaries in a much more sophisticated way. But I think what I'm showing you here will get you 90% there on 10% of the effort. So then we talked about our Cartesian grid. We have a very uniform Cartesian grid, very easy to work with. However, it has some drawbacks, and it turns out a wave propagating through a Cartesian Yi grid actually travels slightly slower than a physical wave would. And in fact, that speed difference changes depending what direction it's traveling. And so it has an anisotropic dispersion, if you will. A second thing that happens is if we have a curved surface, that's slicing through our Cartesian grid, we're forced to have to make a staircase approximation. Now, we've talked about some smoothing and averaging techniques in other lectures, but we're still essentially stuck with this staircase approximation. So those are two big problems with our simple Cartesian grid. It buys us a lot of simplicity, but does suffer these problems. So then we step through a bunch of different alternatives for either conforming to curved surfaces and or reducing the numerical dispersion. So that was last lecture, and now on to this one. And first I want to discuss just periodic structures, not necessarily finite difference time domain yet, but there's some things that we need to know about the periodic structures, the math behind being periodic, that we need to investigate finite difference time domain for periodic structures. Why are we even interested in periodic structures? Well, in modern electromagnetics, a variety of periodic structures, specifically photonic crystals and metamaterials, but also diffraction gratings and other things, they're really dominant structures now. So there's a whole lot of interest in modeling these things that are periodic. We can make waveguides out of periodic structures that are much smaller, can bend much tighter than we could otherwise do. We can make waveguides with near zero dispersion. People are trapping light and slowing down light with periodic structures. Metamaterials, if nature does not give us a material that we're happy with, we can go in and actually structure it, give it physical features that interact with a wave that give that material, at least macroscopically, new and magical properties that we couldn't do otherwise. Instead of making one big antenna, we can put a whole bunch of little antennas cooperating together. That's called a phased array antenna. And we essentially just time when the signal comes out of each element, and we can steer beams this way without actually mechanically moving anything. Frequency selective surfaces is also a periodic structure confined to a plane. This is one of the technologies in stealth. We can absorb waves from the bad guy's radar. Other things we can do, if we have two antennas sitting real close and we don't want them to interfere with each other, we can put a radome over these that block the first antenna but let the second antenna radiate through it. So just a very, very short example of periodic structures. They're all over the place. They're very important, and it's absolutely critical that we talk about how to model periodic structures in finite difference time domain. There are a number of different ways that things can be periodic. We tend to classify them into the 7 crystal systems that we're showing here: the cubic, tetragonal, orthorhombic, monoclinic, triclinic, trigonal, and hexagonal. Within that, there's subsets of those, and if we add all those up, we get 14. And those are called the Bravais lattices. These are the ones that we tend to talk about the most. So the face center cubic, body center cubic, etc. So these are the general ways that things can be periodic. In 2 dimensions, we really only have 5 Bravais lattices. That makes sense. There's one less dimension to have freedom. And so we just talk about our 5 Bravais lattices here. Now we want to start putting some math behind being periodic. And there's 2 ways of creating vectors that describe how things are periodic. One, we have axis vectors. So on the left, we're drawing what we would call our conventional unit cell. And this looks like a body-centered cubic. These axis vectors point along the edges of our unit cell. These very intuitively describe the size and the orientation of the unit cell. However, we cannot uniquely identify all 14 Bravais lattices with those. For example, simple cubic, body center cubic, and face center cubic all have the same axis vectors. So instead, we'll go to what's called the primitive translation vectors. These do uniquely describe all 14 Bravais lattices. So again, we're showing the conventional unit cell, and notice these primitive translation vectors are pointing between adjacent points in the lattice. So that's why they're called primitive translation vectors. A translation vector will point from one site in the lattice to some other point. It could be way off here. And as long as it's pointing from one site to the next, it's still a translation vector, just not primitive. The primitives point between adjacent. And if we've selected these correctly, we should be able to get from any one site to any other site in the lattice just through an integer combination of these translation vectors. If we can't do that, either we've chosen the wrong translation vectors or something else is incorrect. Maybe we don't have the symmetry that we think we have. So these non-primitive translation vectors, they're still called translation vectors, just not primitive. They have to be an integer combination of the primitive translation vectors, and we should be able to get from any site in the lattice to any other site. So here's an example in 2 dimensions. It's just a square array, so we see that we have 2 primitive translation vectors, and let's say we want to get from this site to this site in the lattice. Well, we'll need 3 of those primitive translation vectors and 1 of the other. So this large vector is a translation vector. It is just not primitive, and it is an integer combination of the primitive translation vectors. So we use these primitive translation vectors, very often just called lattice vectors, to describe symmetry within the lattices. So we should be pretty familiar with this by now. A wave traveling through something periodic takes on the same symmetry as the structure that it is in. It turns out there's a little bit more to that story, and in fact it's technically incorrect to say that the field takes on the same symmetry as the device that it is in. The electric field, the total electric field, we really write as the product of 2 things. We have an amplitude term and sort of this plane wave phase term. This plane wave phase term does not have the symmetry of the lattice that it is in. However, this amplitude term does. It has the exact same symmetry as the device that it is in. So since the total electric field is the product of those 2, and the second term does not strictly have the symmetry of the device that it's in, it's technically incorrect to say that the electric field has the same symmetry as its host. It's that amplitude envelope. So what does this overall electric field look like? I describe it as bumpy plane waves. So here's sort of a cartoon picture. We see we've got this bumpy plane wave. We can really assign a direction to it, so it has a direction. But we can set it equal to some kind of bump amplitude envelope and this plane wave phase tilt term. It's this bumpy envelope that has the exact same symmetry as the device that it is in. So what do these bumpy plane waves like? They're actually called block waves. And here we have a periodic structure. We're illuminating at normal instance with a plane wave. And we see these bands of red, blue. So we can see a plane wave characteristic here. That's the plane wave term. But we also see bumps that take on the exact same symmetry as the device that it's in. So that's called a block wave. Same lattice, same configuration, just now we're coming in at an angle. We see that that block wave refracts, so it's traveling at a slightly different angle than the applied wave. But we still see bands of red, blue, and there's definitely this direction of the wave, but it's bumpy. It has bright spots and dark spots. So another example of a block wave. And some block waves look so crazy, it's even hard to discern which way the wave is going. The lower order, the lower frequency block modes tend to look more plane wave-like. They get crazier as we go higher in frequency. So let's put some math back into our periodicity description. Well, if we're in a structure that is periodic, then we should be able to describe the material properties using these translation vectors. So if I look at the permittivity at any point R is just position, and add to it a translation vector, I should get the permittivity just at position R. If the structure really does have the periodicity we're talking about, and it is described by those translation vectors, that has to hold. So if that holds, then the amplitude term has to have the same exact symmetry. And in one dimension, how is this done? We would just add an integer multiple of the lattice periods to position x. And so that should bring us back to just position x, y, z. More compactly, we just wouldn't even write y and z, so we could write our equations this way. So this is the one-dimensional representation, if you will, of these 2 equations. So the material properties and the amplitude term always have the same symmetry, and we describe that the same way with the same set of translation vectors. Now we're armed with the knowledge we need to start thinking about the periodic boundary conditions in finite difference time domain. So we're in the frequency domain right now. We do need to jump to the time domain. So we have our electric field being an amplitude term and a plane wave phase term. We've dropped the z component, so we're restricting ourselves to 2 dimensions here for simplicity. And in our periodic sense here, we're only going to have periodicity in the x direction. Remember how we'll build our grid. We have periodic boundary conditions on the left and the right, and we have PMLs at the top and the bottom. So it's our amplitude term that's periodic in 1 dimension, so we write our periodicity this way. And m is just any integer. And as long as we're adding an integer multiple of the periods of our device, that should bring us back to the same point. So let's think what happens here. Let's look at the electric field at some x plus or minus some period. Well, we put that same plus or minus into our amplitude term because we're modifying x, and so then we also put that same x plus or minus the period term here. Now we're going to group some terms together. We're going to pull out the original e to the j beta x and e j beta y. We'll pull those out. And remember, this is just the amplitude at point x. So we have amplitude at point x with our original terms. So we've pulled out e to the j beta lambda x. That term here came to the outside. Notice this is just the original electric field. So we write that as just the original electric field plus this phase term. So here's how we interpret it. The electric field that's maybe outside our grid unit cell by distance lambda, we can always map that to some point within the unit cell that we're modeling. However, there's this phase term that we have to add to it. And this is the phase across the grid. The transverse phase, if you will. So if we're forced in a finite difference equation to require a field value from outside the grid, we can reach to the other side of the grid and just use that value, but we have to add that phase term in to make it compatible. The boundary condition we talked about so far is a frequency domain boundary condition. So I repeated it up here, and I put the omega term in here to remind us that that is a frequency domain boundary condition. We want to bring this into the time domain because that's where finite difference time domain operates. So let's look at a property of the Fourier transform. If we have a function and we give it a time delay and we Fourier transform that, we get the Fourier transform of the undelayed function, if you will, times a complex exponential with that time delay put in the exponential. So we want to take our original periodic boundary condition and we want to convert this over to the time domain. So how do we do that? Well, we inverse Fourier transform both sides of this equation. Well, if we inverse Fourier transform the left side, we just get this. That's pretty straightforward. If we inverse Fourier transform the right-hand side, what we see, because we have this complex exponential sitting here, is that it's the original function but with some time delay. And then the precise time delay comes out of the Fourier transform math. So that says if we're interested in a field point outside of the unit cell that we're modeling, we can map that to a point within the unit cell that we're modeling. However, we need to grab that value from some other different time. If that tau parameter is positive, we need a value from the future. Clearly, that's going to be difficult since we haven't simulated that yet. If tau is negative, that means we need a value from the past. That's not a problem. We can keep a record of our electric field values and use a value from the past. That's not a problem. So let's think about our periodic boundary conditions for normal incidence. If we have normal incidence, that means our beta x term, the transverse component of that applied wave, is 0. So our boundary condition reduces to this. That exponential term with the beta being 0 up here became a 1, so it's not even there anymore. So that means an electric field value from outside of our unit cell can always be mapped to a point within the unit cell. So here's where we have troubles. Suppose we need the electric field at point 0. Remember in MATLAB it starts at 1. We don't have that. So we're trying to get a value from right here. Those don't exist, but what we can do is reach to the other side of the grid and use a value from this column. Likewise, if we're at the x high boundary, we need a value from outside on the right, so we're over here somewhere. Well, those don't exist. We're not storing them. They're not even in our model, but we can reach to the other side of the grid and use one of these values in its place. So that's the periodic boundary condition at normal incidence. No problem. Now let's think what happens when we have some angle of incidence. So this beta x term is not zero. It's something. We have a wave traveling at some angle. Well, our generalized time domain periodic boundary condition becomes this. And remember, we had an equation to calculate tau on the 2 slides ago. So let's look at the x low boundary. So we need values here at the I index of 0, which is outside our grid. It's not stored. We don't have those. Well, we would like to reach to the other side of the grid. However, we need to reach to the other side of the grid and grab the value from a future time step, something we haven't simulated yet. We really have no way of knowing what that is. So how do we calculate the electric field at a future time step? This is a big problem that there's not really a good answer to. At the other side, we need a value from outside the grid. We're over here. We can reach to the other side of the grid. And here, we need a value from the past. That's not a problem. We can just record these values for as many time steps as we need so that we have this value at a past time step. So this right-hand boundary is not an issue. We can always reach to this side and look at our record that we're recording over time and pull the value from whenever we need it. But if we need a field value on this left side and have to reach to the right, that's a problem because we need a value from sometime in the future in our simulation, which we haven't calculated yet. Big problem. So the conclusions here. A time domain simulation has very serious problems implementing periodic boundary conditions when 3 things exist at the same time. We have periodic boundaries, an oblique angle of incidence, and we want some kind of pulse source. Remember, this is a big benefit of finite difference time domain. We can excite with an impulse, and in one simulation record impulse responses, which contains the frequency response over a huge range of frequencies, all in one simulation. So if we want all 3 of those things at the same time, we have very, very big problems. If we can relax any one of those, there's great solutions available. There is one solution that I know of called the angled update method that if we have all these 3 conditions that we can do, and it works pretty good, but it's limited in the angle that it can handle. We'll talk more about that. All right, case number 1. Let's say we don't have any periodic boundaries. Well, that's great. We put a PML all the way around. We just have our device in the middle, and that's all we really need. We hit it with a wave, it scatters, we record that. There's no problems. Either we're not talking about something periodic or we've included enough periods in this model that, again, there's no problems. If we don't have oblique incidence, our periodic boundaries say we don't need any time delay. We literally can just reach to the other side of the grid without an issue and use the field value from there. So no issues. And this is what we'll do in this class. We'll use periodic boundary conditions on the left and the right, but we'll always restrict ourselves to normal incidence. That lets us use periodic boundary conditions and we don't have to worry about any of this time delay stuff. Now let's say we have periodic boundary conditions and oblique incidence, but maybe we're only interested in one frequency. We don't need the pulsed source. We can excite with a pure sine wave. So we can use something called the sine-cosine method. And in fact, in MATLAB, where variables can be complex, we don't even have to do this. We just can literally let our field values be complex. So they're in the time domain and complex at the same time, which is kind of weird. But in languages, computer programming languages, where the numbers can't be complex, we have to store the real and imaginary parts separately. That's where this was developed. It's called the sine-cosine method. And we essentially iterate 2 grids side by side, one with a cosine source, one with a sine source, and when we need periodic boundaries from one, we actually go to the other grid. And that lets us incorporate periodic boundary conditions for a pure frequency source. Now, the biggest problem with this is we've eliminated one of the huge benefits of finite difference time domain, the broadband nature in one simulation getting the response over a huge range of frequencies. But we get rid of that one, but we do retain all the other benefits. We can still model incredibly large things very efficiently. We can still do all the things that FDTD can do, but we eliminate the broadband nature. So if we want to do a broadband simulation using the sine-cosine method, we're actually forced to repeat a bunch of simulations, each at different frequencies. Well, let's say we have all these conditions. We want a pulsed source, we want oblique incidence, we want periodic boundary, we want all these things. What are some things that we can do no matter how limited they are? Well, we can do something called the multiple unit cell method. And essentially, we're interested in this model here. So we have one unit cell in memory. But what we'll do is we will actually be modeling a bunch of other unit cells this way. So we can have a plane wave traveling at some arbitrary angle. It will look crazy here, so it certainly won't be correct here because we can't do periodic boundary conditions. But as you move away from the boundary or this error region that I'm showing in red, it really does start to look like a nice plane wave at this boundary, and we really can have a plane wave at some angle. Now, we're sacrificing some efficiency here. Instead of just being able to model one unit cell, now we're modeling some number. And it's not always straightforward to figure out how many unit cells we need to have this error region. Then there's another technique called the angled update method. And this is probably the best technique I know of for handling this, but even still, it's a little bit limited. So right now, let's imagine we have a grid. All the field values exist at time equals 1. And so this is sort of our normal finite difference time domain at this point. We could actually go in and update most, but not all of those values. And so now we have most of the values in this grid existing at our next time step, but some of them are still existing at the previous time step. Now we could go in and we could do our next round of updates through most of the grid to the third time step, but leave that little layer of cells at the second time step and the other little layer of cells at the first time step. Now we're in a position we could do the fourth and even the fifth. Notice, by doing this, we've built in this time gradient into our grid. And this is the key for the angled update method. Because remember, at one side of the boundary, we need field values from the past, not an issue. But on the other boundary, we need field values from the future. And since we've built in this time gradient, we can actually grab values from the future, because notice on the other side of the grid, we do have future time values. For example, if we're sitting at the left-hand side of the grid, or I'm sorry, we're sitting at the right-hand side of the grid, but reach over to the left, this value is at a future time step. So it's limited how much of a skew or a slope in the time gradient that we can build in, but there's some things that we can do here. So it turns out, for two-dimensional models, we really can't model an angle of incidence greater than 45 degrees. We're limited to that. And for 3 dimensions, it becomes more like 35 degrees. So as long as we have relatively small angles of incidence, we can use this angled update method. And it's very efficient. It's really no different than the ordinary finite difference time domain. The only thing that happens is we're changing the order of the updates. And so it sort of builds in this time gradient so we can reach to the other side of the grid and grab values from a future time step. So it's very efficient, but limited in the angle that it can handle. There are other techniques. There's a field transformation technique. There's a split field method, and I'm providing the references here. I don't have a lot of experience with these to offer you. They're very difficult to implement. I know stability is an issue with these, but there are other options for you. But in the end, the moral of the story is pulsed sources, periodic boundary conditions, and oblique angle of incidence, all three at the same time. That's a big problem in finite difference time domain. Okay, so on to our last topic. And we will restrict our conversations to talking about calculating band diagrams, but in fact I do get the questions a lot, can I use finite difference time domain to calculate modes in a waveguide? And in fact, yes, and it's really this exact same procedure. We just don't need the periodic boundary conditions at the edges. We can use something else. We certainly can use periodic, but we can use about anything else. But it's done the exact same way. So we can calculate modes in a three-dimensional resonator, modes in a waveguide. Here we're looking at block waves as our modes in periodic structures to construct band diagrams. First, we need to talk about what a band diagram is. So imagine we have this infinitely periodic dielectric, and we have a wave traveling in some direction through this. And so it's traveling through something that's periodic, so it's really a bumpy plane wave, if you will. It's a block plane wave, but we want to learn about these. So it turns out there's a lot of detail I'm not going to cover in this block diagram, but along the horizontal axis it's an array of wave vectors through the lattice. So we're not only changing direction here, but we're changing the period. Because remember that wave vector carries two pieces of information. It carries the direction of the wave and also its magnitude. So what we end up doing is we build our lattice, we construct what's called a reciprocal lattice, and we construct what's called an irreducible Brillouin zone. And if we calculate all of the solutions within this Brillouin zone, we completely characterize the lattice. And again, there's a lot of theory here that I'm not covering, but we cover this in detail in the next two classes following this. To oversimplify it, we really can just think of this axis as being the direction of the wave through the lattice. The vertical axis is frequency. So it's kind of like we're asking the question. We pick a point, we say, okay, this corresponds to a particular wave in a particular direction through the lattice. And we ask ourselves, can this exist? Is there anything like this in this lattice? And so our algorithm says, oh, yes, there is. There's one at this frequency. There's one mode at this frequency, one at this frequency, one at this frequency. And so we just plot points for all the frequencies where that exists. Then we change that wave vector just a little bit, ask the same question. We plot those same frequencies. Those are called our eigenfrequencies. And we keep doing that. And if we step small enough, our points form these lines that we call bands. And we won't get into it here, but there's all kinds of wonderful information we can get out of these band diagrams. And these are the same types of band diagrams that people use in semiconductors that are describing electrons flowing through a semiconductor. Suddenly, we're looking at waves traveling through periodic structures in very much the same way, which is what excited a lot of people. Hey, cool, we know how we can control electrons in semiconductors. That led to computer chips and all kinds of cool things. Suddenly, maybe we can control electromagnetic waves the same way. So that's very cool, and it started a lot of interest. And we can calculate these with finite difference time domain. So let's wrap a black box around how we're solving Maxwell's equations. We know that will be finite difference time domain, but there's other techniques for doing that. And if you take the follow-on class to this, computational electromagnetics, we'll be doing this with a technique called the plane wave expansion method. But the information we give this black box, we tell it what the unit cell looks like, and we give it our block wave vector. There's two pieces of information in the block wave vector. It's the direction of the wave and also the period of the wave, because the magnitude of beta is 2 pi over the period of the wave. So we're asking a question. We say we got this unit cell, and I'm interested in a wave traveling in this direction with this period. What could possibly do that? And out comes a whole list of frequencies that have this exact same relation, that have waves with that period in this direction in that unit cell. Those are what are called our eigenvalues. We can also pull out eigenvectors. These are pictures of our fields. If we plot those, we'll see what the modes look like. And there's an infinite number of them. Now, our models have a discrete number of points, so we're only going to be able to resolve a certain number of them. So we can't resolve all infinite numbers of these. So we wrap the black box around our solver, and we just keep asking for different block wave vectors, a whole list of block wave vectors, and it spits back these frequencies corresponding to all the different modes. And we plot all this and line them up, and we get a block diagram. So here's an animation of conceptually how this is built. So I know we didn't really talk much about it, but this is our Brillouin zone. So this is really the unit cell in this strange reciprocal space that I mentioned. And it turns out there's even redundancy here, and we can whittle it down to what's called the irreducible Brillouin zone. And to be complete, we would need to iterate for block wave vectors filling this entire volume. Instead, what we'll do is we'll just march around the perimeter of it. And so, as we march around the perimeter, you'll see this blue vector here. That's the current block wave vector as we march around the perimeter of the Brillouin zone. On this axis, this is as we're marching that block wave vector. So as we're marching, you'll see, based on the block wave vector's horizontal axis, what it really means over here. And then we'll be plotting all of the frequencies for each of those block wave vectors as we build the band diagram. All right, so let's go ahead and run it. Do it one more time. So again, the blue arrow was our block wave vector. For each choice of those, we plot our frequencies vertically, and if our step sizes are small enough, well, we construct a band diagram. And those continuous lines are called the bands. So it's a little bit odd to be doing this in finite difference time domain. There's some other techniques that are very often better, but there are some clear benefits to using finite difference time domain for band calculations. It's very wide band. A very unique thing about finite difference time domain is that we can account for dispersion. In a frequency domain model, we give it, or the frequency is the output, and so we can't really give it frequency dependent material properties. But in finite difference time domain, we can. That's very unique and very useful because oftentimes the dispersion can really change the property of a device. Frequency domain models, they scale exponentially. So if we double the size of the unit cell, suddenly we're quintupling the number of computations. So it's very excellent for very large, complex unit cells. It's very good for unit cells that have high dielectric contrast or metals. But there are some drawbacks. In order to really accurately identify in frequency where those bands occur, we usually need a large number of iterations. When the bands cross a frequency domain model, that's not a problem. We'll get just two eigenvalues that are the same, but we get two of them. We know that there's two modes there that are degenerate. They have the same block wave vector, if you will. But in finite difference time domain, we're looking for peaks. As you'll see, I have some simulations later. So we can't really distinguish between two modes when they overlap in frequency. And there's also no guarantee that we'll identify all of the different modes. It is easy to miss. Now here, this is very similar to the sine-cosine method, but we're exploiting the benefits that MATLAB can incorporate complex numbers. So we have a periodic boundary condition here, and we incorporate it into Maxwell's equations this way. It goes into the curl equations. We calculate these phase terms, which is the phase across the grid. This is a complex quantity. And these are just the equations, the curl computations at boundaries where corrections are required. And you notice we're incorporating these phase terms in here. So suddenly our electric field values become complex. And that's okay. We're really doing a sine-cosine type of method. So to give you an example of what the MATLAB code would look like, for 2 dimensions, we'll calculate our phase terms this way. And here's the MATLAB code for doing this. We have a phi x and a phi y, and it's just a straight computation. So these are complex numbers. Then let's say we want to calculate the z component of the curl of h at the edge of the grid. We see we have 2 corrections. So here's the code as we've talked about for calculating the curls. We're not using if statements. And I'm highlighting in yellow everywhere we're putting in this correction, and I highlighted in green everywhere we're putting these corrections in. So you can see where they appear. So it's literally just putting those into the model, letting our field values be complex, and it's those boundary conditions that are making them complex, and that's perfectly fine. So I mentioned doing this for band calculations. We have these complex phase terms for phase across the grid. So we're doing very much what will be called a sine-cosine method. And for me, when I was learning this, it was very confusing because I had stuck in my mind that it can't be complex, and I wasn't understanding No, that will just let them become complex. This is similar to the sine cosine method. So, but in Fortran or MATLAB or some language where our variables can be complex, we literally just put those phe's in. We don't have to worry about it. In other languages, we have to separate it, and then it looks like the sine cosine method. So how do we source this? Well, our modes can look very strange. So in fact, what we'll do is we'll incorporate dipole sources that have random position and random polarization. For two-dimensional simulations, the random polarization isn't important because there is only one polarization. But for three-dimensional simulations, we want to randomize the polarizations and the positions. So for example, let's just say we only had one source, but that happened to be at a null of our mode. We wouldn't excite that mode. We wouldn't be able to identify it. So how do we get around that? We just smatter out a random bunch of dipole sources, random position, and random polarization. Then we're going to record the electric fields as a function of time. Again, we want to do this at a number of points and at a number of different polarizations. We want to probe everything. Because imagine you stuck a record point and you only had one of them, and that happened to be a null at a mode. Even if we excited the mode, we wouldn't see it. It's sitting at a null. There wouldn't be any variations in the fields. We wouldn't see it. So similar to how we distributed the sources, we distributed record points. So we want to receive random polarizations in 3D. In 2D, the polarization is not an issue, but we definitely still want to smatter them in position as well. Now at our record points, we record the electric field as a function of time, and we may have a dozen of them, let's say. We Fourier transform each of those impulse responses to get the power spectral density, so we take the absolute value squared of the FFT, then we add them all together to get an overall power spectral density. And if we look at that, we see we have some power spectral density, and it has peaks. And these peaks are the eigenfrequencies, and those are what we'll plot on the band diagram. So here's a movie of what a simulation would look like. On the left is our Brillouin zone. The blue arrow shows our block wave vector. I know that doesn't mean a whole lot to you now. In the middle is our unit cell, and what you'll see is we'll be exciting this with dipole sources, and the fields will go off and do all kinds of crazy things. We'll be recording the fields at random points and adding up and calculating the overall power spectral density as the thing is simulating. And what you can see as it simulates, the power spectral density has more and more distinct peaks that we identify as the eigenfrequencies. So there's sort of a non-linear step in time. It started off slow, and then it's going faster and faster and faster. So you'll see the spectra evolve. But don't expect your simulations to be like this. Again, there's non-linear time steps here. But we just keep running and running and running. This is a windowing thing. The spectra we're looking at is essentially a blurred version of the real spectrum. And so the longer we run it, the more finely we can resolve those frequencies. So that's it. And we have our eigenfrequencies now after we've run it a certain period of time. So let's go on. Now, if we want to calculate what the block modes look like, we have to do two simulations. First, we run a simulation and figure out where our frequencies are. Then, once we identify one of the frequencies, we do the exact same simulation again, except we'll be calculating the steady state field at every point in the grid for the frequency that we're interested in. Or maybe there's even more than one frequency. Maybe we want to calculate what the block modes look like for all of those points. So we do that. And then once we have the steady state field at all the frequencies we're interested in, we can just display that, and we'll get something like this, which is a block mode in a periodic structure. We can see that we have a wave nature, red, blue, etc., but there's bumpiness to it, which we expect. So here's the procedure for calculating band diagrams using FDTD. We build a unit cell on the grid, and we'll calculate a whole list of block wave vectors along the horizontal axis. Then, for each one of those, we'll initialize a bunch of random sources and random record points. We will run the finite difference time domain and record the field values as a function of time at those record points. When that's done, We will Fourier transform each of those impulse responses, if you will, take the absolute value and square to get the power spectral density. We add up all of the power spectral densities from each of our record points, so we have an overall power spectral density, and it's the peaks in that we identify as the eigenfrequencies. Then we go to our band diagram and we plot those eigenfrequencies directly over our block wave vector. And we repeat that for all the block wave vectors, and we've constructed an electromagnetic band diagram using finite difference time domain. So here's an example of a three-dimensional simulation comparing what I get from a different technique called the plane wave expansion method to finite difference time domain. We can see that really it's calculating the same thing. Now here's one final animation of FDTD actually doing everything, calculating the entire band diagram. The faded green lines on the right, those are the bands calculated with the plane wave expansion method. That took about 1 second. With finite difference time domain, it took probably several hours. I wasn't around. I just kind of let it run and walked away. But let's watch this run. So we see a simulation happening in the upper left. We're watching the power spectral density evolve in the lower right. And when it's done running, we pull off those peaks and we plot them in the band diagram. So it's really a series of the movies we showed in a previous slide. So I will stop my talking and let this run. I guess I'll point out a few other things. On the lower left, I'm showing the power spectral density as it evolves during each simulation. Again, there's a hugely nonlinear time step happening here. But vertically on the band diagram, I'm showing those exact same peaks being identified. And at first, there's a whole bunch of peaks. But as it simulates and the power spectral density evolves, a lot of those peaks dip down to be an insignificant number and we can ignore them. But it is very common that we will identify peaks here that don't correspond to bands, or there's something artificial, or we miss a band. If we go back and we run this with only one source point, for example, we'll definitely miss a lot of bands because we're probably exciting it either in a null or so close to a null that the power in that mode dips down to a point where we ignore it. You'll notice there seems to be some discretization in the positions of the eigenfrequency here that we're getting from finite difference time domain. And that's because of the number of iterations we have. There's only so finely that we can resolve the frequencies. So we see the discretization from that. If we wanted that to look smoother, then we would have to run for more iterations. And we've talked about in previous lectures how many iterations we need given a certain frequency resolution that we want. You're typically not limited here in the upper frequency limit. The limit more is how many iterations is needed to identify the bands accurately and to resolve the frequencies as accurately as you want. So I mentioned when I calculated the bands of the plane wave expansion method, this took about 1 second. And the FDTD, I wasn't around for it, but it took at least several hours, although it was creating a movie also. So but let's say it would take an hour or two. So it seems like the plane wave expansion method is a rocket ship compared to finite difference time domain. And for this simple unit cell, that's absolutely true. However, make this unit cell very large. Make it, maybe it's 10 by 10 unit cells or 10 by 10 wavelengths, and put some really high contrast in there. Suddenly we would see finite difference time domain become the faster method. because the plane wave expansion method scales so exponentially, whereas the FDTD only scales about linearly. Meaning, if we double the size of the problem, it just doubles the number of computations, so it scales linearly. That's not the case for the plane wave expansion method. So remember, as we're marching left to right in this band diagram, we're changing the direction of that block wave vector. And that's being plotted as the blue arrow within that Brillouin zone that I've shown. And so we're marching from the gamma point to the X point to the M point, and then here we'll start marching back to the gamma point. So we will skip to the end here. You get the point. If I can make it skip to the end. There we go. Okay, so we'll end it here. You get the idea. We can calculate band diagrams. So that is it for this lecture.